fluxural member, that is beam. In this lecture, we'll understand the design steps involved in solving laterally supported beam and laterally unsupported beam. In laterally supported beam, there are two conditions, low shear and high shear condition. The steps to solve low shear condition is available in page number 53. And this low shear condition is expected when the maximum shear force is less than the 0.6 of VD. When it is greater, then we go for a high shear condition. Before getting to the design steps, there is some basic note that is given here. That is the formula for maximum bending moment, shear force and deflection. These formulas you have already learnt in your earlier semesters. So there is nothing much to discuss on this. So directly moving to the design step. To step 1. At the step 1, we have to note down the material properties and partial safety factor. That is, we have to note down Fy, gamma m naught, gamma m and Fy m. Sorry, it is Fyw. So, what is Fy and Fyw? These Fy and Fyw are the yield strength of the steel. So, it is 250 Newton per mm square. And gamma m naught and gamma m are the partial safety factor for the material and for the load. These two are available in table number 5. These two are this table number 5. Partial safety factor gamma m. So it is for materials gamma m. So resistance governed by yielding gamma m naught, it is 1.10. Okay. So this value you have to take into consideration. Next is the step 2 is a load calculation. So what is a load calculation? First we'll assume a self weight of the beam as 0.8 to 1 kilonewton per meter. Now we can calculate the total load. Total load is a dead load plus live load plus the self weight of the beam. Dead load and live load would be given in the question. Self weight you assume and you identify the total load. Now total factored load will be total UDL multiplied by gamma f. Gamma f is equal to 1.5, that you know already. So we can obtain the total factored load. Once this is obtained, the step 3 is the maximum bending moment and the shear force calculation. So for simply supported beam with UDL, it is WL squared by 8. If it is point load, WL by 4. And for shear force, simply supported beam with UDL, it is WL by 2. And if it is point load, W by 2. So we can calculate M and V. Next, the step 4. Step 4 is the calculation of the plastic section modulus. This can be calculated from the formula given in page number 53 at the under the clause 8.2.1.2. So if you see here, page number 53, 8.2.1.2, it is clearly mentioned MD is equal to beta B ZP Fy by gamma m naught. So beta B is equal to 1 for plastic and the compact section. So, in the beginning of the problem, we assume that our section is a plastic section and the moment that the section can take up would be the maximum moment. So, MD will become M and beta B will become 1. So, the formula will be redesigned as what? MD is equal to ZBF by gamma m naught, from which we can obtain set P is equal to M gamma m naught by Fy. Here MD is replaced by M and beta is equal to made as 1. So from this formula we obtain the plastic section modulus. We know gamma m naught is 1.10 and Fy is 250 Newton per mm square. Now the plastic section modulus is identified. Next step, that is step 5, would be the selection of the section. So how do you find the selection of the section? You have plastic section modulus with you right now. So page number 138, table 138, page number 138, table 46. So if you see in the table, we know the plastic section modulus. So having obtained some value, state for example, you have obtained a value 3570. Then, 3500. So you choose a value 3510 that is a bit larger than the obtained value, and you choose the section. So it is ISMB 600, right? So after obtaining this section, you have to note down the D value, BF value, TF value, TW value, and ZD value, and the new ZP value. Okay. So all these value you obtain from this annexure H. But we don't have IXX and R1 value in this particular code book. So this can be obtained from the steel table based upon the section that you have chosen from this IS 456. Okay. So select I section having plastic section modulus more than the required ZP. Required ZP is the one that you have calculated using this formula in the above step. And note down the properties of the section such as D, BF, TF, TW, ZT and ZP. So having obtained this section with the same section, state for example ISMB 600, you go to the steel table at the page number 2 or 3, it will be available. So in that you choose the R1 and IXX value from the steel table. So this is the selection of section is over now. Now the step 6 is the calculation of the beam section. Now we have to check whether our section is a plastic section, compact section, semi-compact section, that you have to choose. So for that calculation, we need to calculate epsilon, B by TF and D by TW. So we don't have B value directly from the code book, whereas we have BF. So from the BF, we can calculate B. B is equal to BF by 2. Then adding to that, we also don't have D value from the code book. So this can be obtained using the formula D minus 2 into TF plus R1. So R1 that you obtained from the steel table. Rest of the other values you have obtained from page number 138, table number 6. So these things. So now based on B by TF, using the table 2 available in page number 18, we can classify the section. So this is a table. So what is given? Epsilon is equal to 250 by F5 the whole power 1 by 2. So ours is a compression element, outstanding element of compression flange and web, flange and web. So here it is roll section B by TF. So based upon the B by TF and the obtained values, you can calculate epsilon. So obtained value, which two values are matching. If this value is matching with this plastic condition, then it is said that our section is a plastic section. If B by TF value matches with the compact, then it is said to be a compact section. If B by TF value matches with a semi-compact, then it is said to be semi-compact section. This is how we classify the beam section. So once the beam section is classified, we move to the check. Various checks we do. So at the first step, what did we do? we have at the step 1, what did we do? We noted down the material properties and factor of safety, then the load calculation, maximum bending moment and the shear force, then we calculate the set P value, that is plastic section modulus, and with the plastic section modulus we selected the section. When once we selected this section, we did a classification of the beam section that we have selected, and after this is done, we will be going to various check. The first check is the check for shear. This is available in page number 59 under class 8.4. So the condition is V should be less than equal to VD. Then it is said to be, that is, our section is safe for shear. That is, it is okay. So what is VB? We know we have calculated this step 3. What is VD? VD is the design strength. So design strength is given by the formula Vn by gamma m naught. So Vn and Vp are one and the same. So Vp is equal to AV Fy W by root 3 m. So from which, what is AV? Where AV is equal to area, H into TW. Note here H would be the total depth D, and FYW will be 250 Newton per mm square. See, this is totally available in page number 59 of class 8.4. If you see 8.4, see the condition, it has to be V should be less than VD. What is VD? Is a design strength, and it is given by the formula Vn by gamma m naught. Gamma m naught you have obtained from the table number 5. So what is Vn? Nominal plastic shear under pure shear. That is, if it is a plastic condition, Vn is equal to Vp. So what is Vp? AV YW by root 3. So this is the area, that is D into TW. Substituting all this, we can obtain the value of VD, and this can be checked. V should be less than, if it is less than VD, then the shear is, it is the selected beam section is safe in shear. Okay, so this is a check for shear. Now, having done this test, we have to check whether it is a low shear condition or the high shear condition. In the low shear condition, the condition is V should be less than 0.6 VD. If it is V is less than 0.6 VD, then the low shear condition has to be considered. If it is greater than 0.6 VD, then we have to go for high shear condition. See, for low shear condition, it is in page number 53, class number 8.2.1.2 and 8.2.1.3. So, in page number 53, class 8.2.1.2 and 8.2.1.3, when the shear, design shear force, that is factored shear force, V exceeds 0.6 VD, where VD is a design shear strength of the cross section, the design bending strength MD shall be taken as MD is equal to MDV. So this will lead to the high shear. This is the low shear, and when this condition exists, we have to move to high shear, and it is available in the clause defined in clause 9.2. Where is 9.2? It is available in page number 69. If you go to page number 69, again it is repeated. No reductionist moment capacity of the section is necessary as long as the cross section is not subjected to high shear force. That is, like, there is no reductionist needed. But if it is exceeds, then we have to go for this high shear condition. When the factored value of the applied shear force is high, the factored moment of the section should be less than the moment capacity of the section and a high shear force MDB calculated as below. So these two formulas we have to use. So it is discussed here. So for your convenience, I have shown both the things at one particular area. So step 8, check for design bending strength. For low shear condition, we are checking page number 53, 8.2.1.2, the same formula. The condition has to be as same as that of the shear. The maximum bending moment should be less than equal to MD. If it is that, then it is the condition is okay. That is, the section is safe for moment. So MD is equal to beta B, Z Fy, gamma M naught. This is available in page number 53. This we have seen, right? Page number 53, the same formula. Page number 53. So in this code book, it again in the below paragraph, there is something that they have written. To avoid irreversible deformation under serviceability load, MD shall be less than 1.2 ZEFY by gamma M naught in case of simply supported and 1.5 ZEFY gamma M naught in cantilever beam condition. So now it is simply supported condition only, generally it comes, right? So we go for this check also. So totally there are two checks. M should be less than equal to MD and another check is equal to MD should be less than 1.2 ZEFY by gamma M naught for simply supported. MD should be less than 1.5 ZEFY gamma M naught for cantilever beam. So beta B is 1 for plastic and combat section given in the code book. Beta B is equal to ZD by ZP for semi-compact section. ZP is the plastic and ZD is the elastic moduli of the cross section respectively. Okay, see everything is given here. Beta B for semi-compact, ZP, ZE, Fy is the yield stress of the material, gamma M naught is the partial safety factor. Everything is directly given in the code book. So this thing we have already taken. So Fy 250 Newton per mm square, gamma M naught from table number 5, page number 30. So when these two checks are done and if it is coming less, then it is condition is safe. Whereas, okay, now this is low shear case. Whereas if it is V at the first step, the maximum V is greater than 0.6 VD, then we have to go from this case to this case. If it is less, we went for this case. If it is greater, then we have to go for this case. So condition for this is available in page number 70. So it is available in page number 70. A and B, two things are available. So you see the formula MdV is equal to MD minus beta MD minus M FD less than equal to 1.2 ZDFy by gamma M naught. So beta is equal to V by VD minus 1 the whole square. MD is equal to the plastic design moment. V is a factor applied shear force. VD is a design shear strength. MFD is a plastic design strength. ZD is the elastic section modulus. This is for plastic or compact section. If it is a semi-compact section, then MdV is equal to ZDFy by gamma M naught. These are the directly formula. So this formula, these are the things that we needed. So one place we have to put our brain is ZFD. What is ZFD? ZFD. We have, right? MFD is equal to plastic. See here, this one. MFD is equal to plastic design strength of the area of the cross section excluding the shear area, considering the partial safety factor gamma M naught. So excluding the shear area, considering the partial safety factor. So this is the MFD formula. So this is ZFD is coming. ZFD is equal to excluding the shear area, and considering the partial safety factor gamma m naught, and that is MFD. So XFD is equal to ZP minus 2 into 2 in, because there are two flanges. So 2 flanges into length of the web. So here we are just taking the 2 outside. So this half we have taken, okay. Length of the web, the total D divided by 2 will be this half, into thickness. Thickness is TW, into centroidal distance. Now from here to this center, right? So it is D by 4. So ZFD is equal to ZP minus 2 we have 2 webs, no? So we are calculating for 1/2 and multiplying it 2. So 2 into length of the web into thickness into centroidal distance. So ZFD is obtained. ZD you have already calculated from page number 138, table number 46. So with this, once ZFD is known, we can calculate MFD. Once MFD and MD is known, then we can calculate MDV. When MDV is known, we can check this condition, if it is okay or not. This is for the plastic and compact section. If it is a semi, then MDV is equal to ZD. ZD you know from page number 138, table 46. FI you know, and gamma you know. This value you can calculate, substitute over here and check for the condition. So this is a high shear case condition. And done. So this is a place where we have to put little more effort. Once after the check of the shear is done, we have to check whether it is lying on the low shear case and or in the high shear case. And based upon this low shear condition or high shear condition, we have to do the check for the bending strength. Now the final area is step 9, that is check for the deflection. So deflection, the condition is delta max should be less than delta. So delta max, what is the formula? Maximum delta for simply support is 5 by 384 WL power 4 by EI. And if it is 0.4, WL square by 48 EI. So permissible deflection, this has to be obtained from table number 6. Table number 6 of page 31. So if you go to table number 6 of page 31, other buildings, like this is vertical. There is two things, industrial building and other building. As is like simple building or vertical building. So vertical, floor and roof. Okay. Floor and roof. So element not susceptible to cracking. What is given? Span by 300. And so we have taken for span by 300 for simply supported beam. So if it is for cantilever, then span by 150. But our case, mostly it will be span by 300, simply supported only. So this will give you the permissible deflection. That will give you the maximum deflection. So with that we can do the check. If it is delta max is less than delta, then the deflection, the section is safe for deflection. The final is the check for web buckling and web crippling. So the condition is what? This is available, FW should be greater than V. So FW, where it is available in page number 67 at clause 8.7.4. Here, 8.7.4, FW is equal to B1 plus N2 TW FYW by gamma M naught. B1 is a stiff bearing length. N2 is a length obtained by dispersion. And TW is the thickness of the web, and FYW is the yield stress of the web. Okay. So B1, it is always assumed to be 100. N2, we can calculate 2.5 into TF plus R1. FIW, it is 250 Newton per mm square. Gamma M naught, it is 1.1. Okay, so this is a condition for web buckling, crippling. When, now one small note is like, small check that has to be done for web buckling is if d by tw is greater than 67 epsilon, the buckling is there, else there is no buckling. This is a small understanding that we have gained from the knowledge at page number 59. At page number 59, 8.24, 2.1, it is simply written, resistance to shear buckling shall be verified d by tw if it is greater than 67 epsilon for web without stiffness and with stiffness. As is like there is no stiffener at the top, it is only a simple I section. So this condition, if this condition is checked, that is d by tw is greater than 67 epsilon, then buckling is there. If there is, it is not exceeding, then there is no buckling. Okay, that sentence you can say. So that is how, these are the 10 steps that has to be followed to solve problems of laterally supported beam section that under low shear or high shear conditions. Okay, thank you.